In Chapter 8, we're going to be discussing multi-step mechanisms. So these are going to be the mechanisms for reactions that contain more than one elementary step. In this section of Chapter 8, we're going to specifically focus on those multi-step mechanisms and the kinetics associated with our reactions. So first off, multi-step mechanisms are going to combine multiple elementary steps together to design a theory on how reactions take place with the bonds being broken and the bonds being formed. What we're going to discover is that most of our reactions don't take place in one elementary step. We break and we form bonds in a series of steps as we convert from the reactants to the final products. So our mechanisms can actually become very long and complicated when we look at an overall net reaction. The first multi-step mechanism I want to look at is going to be an SN1 mechanism. So we've already discussed the SN2 mechanism in our previous chapter. So this we want to look at an SN1 mechanism. This SN1 stands for a unimolecular nucleophilic substitution. So that 1 stands for unimolecular, which means that we only have one molecule reacting in our rate determining step. So what we're going to be looking at with this SN1 mechanism is we are going to have our substrate, and that substrate is going to contain our leaving group, just like we saw in our SN2 mechanism. But this time for this mechanism, since it is an SN1 mechanism, that leaving group is just going to leave. We're not going to have anything else pushing it off. The leaving group will just leave, which leaves behind for us the carbocation that we generate, plus the negatively charged leaving group that has left. So this becomes one step in our mechanism. But for the overall reaction, we can't end with a carbocation. Carbocations aren't that stable. It's not something that we would isolate. So the next step in this sequence would be that our carbocation is going to react with another nucleophile that we have in solution. And this becomes a second step in our mechanism. So it becomes a multi-step mechanism for us. If we combine both of these for our net reaction, the net reaction looks very similar to what we saw before, where we have our substrate with the leaving group reacting with a nucleophile to see a substitution of the nucleophile in place of the leaving group. So the net reaction is similar to the SN2 mechanism that we looked at, but the difference is with the SN1 mechanism, it's a multi-step mechanism. It happens in two parts. First, the leaving group will leave, generating this carbocation. That carbocation will then react with the nucleophile to form the final product. So we have a multi-step process. In these multi-step processes, we end up forming an intermediate. That carbocation is an intermediate. Usually these intermediates cannot be isolated. If you'll notice, they're not part of the net reaction. It is something that we generate in between the reactants and the products. Sometimes they can be isolated, but usually they're high energy species that cannot be isolated. They are going to be higher in energy than both the reactants and the products. What you do want to recognize is that intermediates are very different than our transition states. Intermediates are true compounds. They contain only bonds. They don't contain partial bonds like the transition states. They contain bonds. Oftentimes they are particles that have a charge associated with them, which is what makes them higher in energy. But you do want to recognize intermediates are very different than transition states. So we looked at our free energy diagrams in a previous chapter for a single elementary step. I now want to put this into the context of our multi-step reactions with our energy diagrams. So we're still going to start off with our reactants, but what's going to change is, since it is a multi-step mechanism, those reactants initially produce our intermediates. Those intermediates then react again to finally produce our products. So you'll notice in a multi-step mechanism, we have two curves with it, which means we have two transition states. I have a transition state as we go from the reactants to the intermediates, so step number 1 in our mechanism. I also have a second transition state that happens as I go from the intermediates to the final product, so the second step in our mechanism. Those two transition states will be very, very different for us. So you do want to recognize that when we have multi-step reactions, they show up as multiple curves in our free energy diagrams. So if I had a mechanism or a reaction that took place with 3 elementary steps, I would have 3 curves and 2 separate intermediates that we would be looking at in our free energy diagram. The next multi-step mechanism I want to look at is going to be our E1 mechanism. Our E1 mechanism stands for unimolecular elimination. So this is going to be similar to our E2 mechanism that was our bimolecular elimination. We're still going to be eliminating things from our substrate, but in this one we're going to do it in a multi-step process because once again we're looking at a unimolecular elimination, which means we're going to be dealing with one molecule in our rate determining step. So for this process, once again we will have our substrate. And in our substrate, we have a hydrogen and a leaving group on adjacent carbon atoms. Once again, in this E1 mechanism, that leaving group is just going to leave the substrate, and that is going to leave behind a carbocation, as well as our negatively charged leaving group. From here, in the second portion, or the second step of our mechanism, we are going to have that carbocation react with our base to deprotonate that hydrogen that was on the adjacent carbon atom. As that happens, those electrons will go in to produce that alkene that we produce through our elimination process. So our final product will be the alkene, and then we have that protonated base as well. So once again, if you look at these, if we combine these into the overall net reaction, our net reaction will be very similar to what we saw with our E2 elimination that happened all in one step. So we have our base reacting with our substrate, and again in the substrate we have our leaving group and our hydrogen on adjacent carbon atoms. We then end up with our protonated base plus our negatively charged leaving group as well as the alkene. So the net reaction is just a sum of these 2 elementary steps, but in an E1 type mechanism we do see this multi-step process where once again we have produced the carbocation intermediate in step number 1. That carbocation intermediate will then react in step number 2 to get us to our final alkene. So one of the ways we distinguish between the different types of mechanisms, the SN1, the SN2, the E1, the E2, is going to be through our reaction kinetics. The kinetics is really going to dictate how many steps we see our mechanism go through, since the net reactions were the same for the SN1 and the SN2, for the E1 and the E2. We use kinetics to help us distinguish which mechanism we're going to see as we go throughout a reaction. So with our reaction kinetics, from your freshman level course, you were taught about rate laws. Rate laws are laws that correlate for us the initial concentration of the reactants to the overall rate of the reaction. One of the things that we're going to worry about with rate laws is that if we have an elementary reaction, the reaction orders in our rate law are going to be equal to the reaction coefficients. So in organic chemistry, when we start talking about our mechanisms, remember every step in a mechanism is an elementary reaction. It's an elementary process. So in those steps, we can use those reaction coefficients, which are typically 1, to become the reaction orders in our rate law. What we're going to see with these rate laws and why they become important for us for dictating the mechanism that we use for our overall reaction is that in a multi-step reaction, the slowest step is what's going to determine the net reaction. So if we look at the rate law and the relationship between concentrations and the rate of the reaction, by looking at the rate law, we know what the rate determining step is. We can state, is this going to be a unimolecular reaction or is this going to be a bimolecular reaction based on the rate law itself. So just for the SN1, SN2, E1, and E2, so we can look at a comparison between them. The rate law for an SN2 mechanism, since it is a bimolecular reaction, the rate is going to be equal to K times the nucleophile times the substrate with the leaving group. It is bimolecular, so the concentration of both the nucleophile and the substrate are going to impact the overall rate of the reaction. But if we compare this to our SN1 rate law, That rate law is only that the rate is equal to the K value times the substrate with the leaving group. Notice the nucleophile does not play a role, because in that first step in our elementary reaction, the leaving group just leaves. It is not driven off by the nucleophile like it is in an SN2 mechanism. So the rate determining step is only dependent upon one molecule. And that's what tells us that we have that unimolecular reaction and we would have a multi-step mechanism. The E2 and the E1 have a similar relationship. If we look at the E2 rate law, the rate is equal to the rate constant, the K value, times the base concentration times the substrate concentration. Again, it is bimolecular, so we're looking at a relationship between both the base concentration and the substrate concentration. Where with our E1 rate law, the rate is equal to the K value times just the substrate with the leaving group. Because remember, again, in our E1 mechanism, it is unimolecular. The leaving group just leaves in the first step of our mechanism, and then the base comes in and we form the alkene. So because of that, we have a unimolecular rate law. So if we know the rate law for the reaction that we are dealing with, we can go back and we can predict, will this be bimolecular, will this be unimolecular, and it will help us dictate what the mechanism is. Just to review again quickly, that K value that is showing up in all of our rate laws, that lowercase k value is the rate constant. What the rate constant gives us information about is kind of the rate at which the reaction will happen. So the larger the K value, the faster the rate. The smaller the K value, the slower the rate. One of the other things to remember from your freshman course is that these K values are going to be temperature dependent. If we change the temperature, we change the K value, and we can change the rate of the reaction as well. What we will always see is that the higher the temperature, the faster the rate for our reaction. So rates are still going to be temperature dependent, and in our law, the temperature dependent aspect is going to be that rate constant. So now let's put this also in the context of our free energy diagram and how we can use our free energy diagram to also help us predict rates of reactions and steps of reactions as well. So if we look at our free energy diagram, we have our energy, we have our reaction coordinate. I'm going to look at a multi-step process where I'm going to take my reactants, I'm going to convert them into my intermediates, I'm then going to convert those intermediates into my products. So again, I've got a multi-step mechanism and I would have two transition states. The transition state as we go from the reactants to the intermediates, and the transition state as we go from the intermediates into the products. So from here, we want to fill in the other pieces that we know for our energy diagram. The biggest one is going to be our free energy of activation. So remember, our free energy of activation is going to be the reactant energy up to that transition state energy that we have been dealing with. And really that tells us how much energy, the barrier that we have to get over in order for the reaction to happen. But now since I have a two-part process, we have two free energies of activation. I have one for the first step, and I also have one for the second step. In the second step, I'm going from those intermediates up into the transition state for that step as well. And what you'll want to notice is that they are very different in terms of the energy barrier that we have. The first step in this mechanism has a very high energy barrier. The second step has a very low energy barrier. And this now helps us predict what is the rate determining step, what is the slower step. And what we're going to see is that the larger that energy of activation, the slower the rate is going to be for that step. So these energy diagrams, we can use them to help us predict what is the slowest step, what is the rate determining step, what is the step that's going to dictate our kinetics. And in this reaction that I have drawn on the board, it is going to be that first step that is going to be the slowest step. It is going to be the one that dictates the rate of the overall reaction. So if this were an SN1 mechanism, it would be that first step with the substrate and the leaving group just leaving that substrate. That's what's going to predict our kinetics. It's what's going to predict the overall rate of the entire reaction. The easiest way to remember that it's the rate determining step, the slowest step that dictates all that, is that in a relay race, the relay runners can't be any faster as a whole than the slowest runner that is on the team. So we're going to be doing the same thing here. Our net reaction cannot be any faster than the slowest step, and that will be the step that has the highest energy barrier.